All right, shall we get started?
Yep.
Yeah, Mule.
And do a quick introduction for you and Tommy while people still stroll in. So it's 2:00 p.m. I'm Ken Gracie. I'd like to welcome you to the second progress meeting of our joint curriculum effort with cyber.org. And we're very thankful for their support. They're here today with us. This is our pre-engineering curriculum planned for release this summer entitled What's a Microcontroller with Python and the Microbit. And this will move students along from where they are, making things go, making them have sound and blinking, to understanding the voltage, current, measurement, and the real engineering behind this. So this will move them to the next level because the new microbit can do it. It has lots of memory for Python and lots of cool stuff built onto it. So today our host and author Andy Lindsay will provide a progress update with his co-host Tommy Gober of cyber.org. If you're watching this on YouTube, there is a part 1 that we had a month ago, and the YouTube description on this video provides a link to the first meeting so you don't have to watch things out of order. So as the ground station controller, I'm checking out and turning it over to you two guys. Andy Lindsay.
Thank you, Ken. So I hope you're all doing well today and that you enjoy this next installment on the progress report here. And how's my screen look? Am I sharing the right screen? Okay, we got a slideshow. Good. All right, so here we are for part 2. Quick recap on part 1. We talked about the topics, the software that we'll be using with the lessons, went through and explained how What's a Microcontroller will be focusing on circuits that go into typical products, which also can be used in inventions. And so understanding how they work and what they do inside a product and how to make them do it is also a great piece of information that students can use to invent their own goodies. And so we went through the parts, typical. It's mostly the usual stuff, and I probably should avoid recounting the parts because that's a long list. We talked about the visual support elements that are part of the lesson, and let's see here. There we go. So this is an example of one of the things, just as a memory refresher. This animated GIF is meant to help students really get how two wires are either connected or not connected, depending on whether they share the same row of 5 sockets or not. And so this is an example of some of the extra work that we're doing just to make sure that we can get important and fundamental concepts across, so that it basically just reduces the boundaries to learning. So that's one of the things we went over in detail. And another item for visual support is when we're showing how to build a circuit, we're actually adding parts and building the schematic at the same time, so that students can kind of develop a relationship between the parts and connecting them together, and then how that relates to a schematic. And then we had the Educator Preview, which has Ken mentioned is on YouTube. And since we covered a lot of material, and so anybody who has not seen it but is still interested after what you see today, I highly recommend going and taking a look at it, because it covers a lot of ground and it explains quite a bit. Today, I'll be focusing a lot more on how the material will be used, as opposed to what is it, what's it about, what are we doing to get it across to the students better, and that kind of stuff. We got your feedback on how and what to make available, and implemented that. One thing I have not been doing is posting lessons on regular intervals. I was a little bit more focused on software development between the last meeting and now. And we're going to talk about that quite a bit today, as in using the software that we've been developing. And then today, after this, I'll be able to check this off because we've got 10 or so lesson skeletons for you to try out. And I'll be demonstrating quite a few parts from that. And then we'll be able to check this one off too, since that's happening right now as we speak. All right, so let's talk a little bit about cyberscope.parallax.com. This is a web application that makes it possible to use, it basically allows the microbit to take the place of some of the common measuring tools like a voltmeter and an ammeter, ohmmeter, oscilloscope to measure parts of circuits. And in right now, looking at the electronics education and robotics education landscapes, there really isn't much measurement going on. It's much more focused on, hey, build the circuit. This is what it did, gee whiz, and then move on. And so what this is designed to do is, one, teachers don't necessarily have to go and buy a multimeter and an oscilloscope to have the students have the experience of using those items. And then two, it just makes it available for the lessons, and by using them and measuring and taking a moment to take some measurements on each circuit you build, what it does is it helps gain a deeper understanding of how the circuit works. So just a quick thing, you can go to cyberscope.parallax.com, and it even has a little built-in video that basically shows, if you have a microbit, how to use the demonstration Python script to display some data. And so that's what this little clip is doing right now, is it's showing how to download Try Cyberscope, which is linked to the page, and then how to open it with the online Python editor, and then flash it into the microbit and disconnect. Now, the important thing is, notice here, when we connect, it's the same process as with the online editor. I thought that was really important. And so this is just pure data that's being sent. It's not actually measuring it, but it gives you just the opportunity to see some of the stuff that the Cyberscope can do. I see that Chip Gracie is here, and so he might be curious about the bandwidth, and it's a tiny fraction of the bandwidth of a normal oscilloscope. So it's mainly for the sake of having a first experience with an oscilloscope as opposed to an actual diagnostic tool. And with a $20 microbit, that's cool.
Yeah, it's an instructional scope. It's not any production, but if you cut your teeth on this, when you take off the so-called training wheels and you get onto a real scope, then you'll be, familiar with the purposes of it and being able to, explore more as you get more further down the road.
Yeah, having had a first experience with it here is what I'm hoping will help students who end up in either technical schools or engineering programs not feel quite as lost when they get there. Because I remember for myself, it was a tough learning curve the first time in the lab using an oscilloscope, because I did not have one at home or was not a hobbyist or anything like that. So that's an example of getting started with the Cyberscope. And now let's take a look at some of the activities. And I'm actually going to go through these and just give you a stream of consciousness, anything I notice about each activity. And by the way, I want to make sure you all have this web page chat to everyone. Paste. There we go. All right, so slide 3 is our main slide. And what I'm going to show you through this is, let's see, we have, oh heavens, I forgot to share this out. Oh boy, let's see. Okay, file, share. Try one more time. Anyone with the link? Done. All right. Hopefully now you guys can get into that, get into the document. Sorry about that. I looked at it at least twice before this started and thought, man, I got to share that before the.
Don't forget to share it, Andy.
Thanks.
We'll time warp it and then edit the video later.
Actually, we have a feature in this oscilloscope that may provide the key to getting that done. More on that in a little bit. All right, so let's first take a look at measure voltage. It's basically the next step after what is already on the web, which I'm going to back up a little bit. So we talked about during the first session an example chapter, and it is already on learn.parallax.com minus the questions, exercises, projects, and solutions for the teachers. So this is already available to look at. And then what's coming up next is is we've got basically I'm going to group together measure voltage, resistance and current as a chapter. And so what I'd like to do is show you how that works. Let's see here. Okay, we'll do 100% there, and then that might be a little bit too zoomed in, I guess we'll see. So here again is some of the visual support that that we're adding to the lessons. And there's quite a bit going on here. So having it be an animated GIF, and there's also an MP4 of it. And the MP4 is nice because students can open it and basically hit pause between each step. And so what you're seeing here is that the students are taking measurements, voltage measurements, at different points in a circuit they've built. It's their first DC light emitting diode circuit. And the schematic version of probing the circuit is shown. And also the voltage measurement from the Cyberscope is shown. And so this gives students an idea of what to expect when they're doing the activity. And it also segues into things like how to calculate how much current is going through the circuit, Kirchoff's voltage law, because you can add up the voltage drops of these two components, and it is equal to the voltage across, or the supply voltage. Let's see here. So what I'd like to show you is that most of the starting lessons have a pre-written script, and it's distributed as a hex file. And the reason for that is because there's a module under that we can store in the hex file, and that module makes it possible to, well, basically, we don't have to walk everybody through instructions on how to add that module every time. They can just download the code that has the module in it, and it just downloaded. It's over here, measure volts. And then once they've downloaded it, they can open up python.microbit.org. And I'm going to use the beta version for this. All of this is 3 months out, so there are still some things that the beta fixes that are not necessarily working in version 2. I might try to give you an update of that later when we get to the Servo part. We'll see whether it makes a difference anymore, whether we're in beta or just plain old version 2. All right, so here we are, and we downloaded measure volts. Now, if you have a Mac, if you have a Windows machine, or I think a Chromebook, you can just drag and drop the file you downloaded into the editor, and the script comes right up. If you have a Mac, you may need to click the Load Save button and then drag the file you downloaded and drop it on this. Let's see, what's it called? The drag and drop box right here. I've noticed this with Mac, but not with Chromebook or Windows. All right, so once you've got the once you've got this in the editor, it's again the same thing you saw on the video of clicking connect and then flash and then disconnect. And I'm going to make an intentional mistake here and try to go to, and these are all things that are in development currently, and then by mid-June, we won't see these kind of problems. But if I just go to plain old cyberscope.parallax.com, it's going to present me with a red banner saying, sorry, we can't do that. And the reason is because Web Serial for Chrome is not supported under the not secure protocol. I believe that in our list of bugs and enhancements that we want to auto redirect to the secure version from here. So you have to type in https:// if you want to try it out. And then we don't get any red banner. Okay, so I've already loaded the script into the into the microbit by just going to repeat that real quick here. Okay, so this script right here is what we loaded into the microbit. And so now that script, actually before connecting, I'll show you something really quick. If you open Serial here, you can see the key value pairs that the microbit is sending to the Cyberscope. The Cyberscope will take a look and say, oh, look at that. I'm receiving a key value pair that has a V in quotation marks. And that must mean that I want to view this data in the voltmeter. So disconnect here and then connect here. And one important thing is that, did you notice that as soon as I hit connect, it went straight to the voltmeter? That's something that I felt would be important for students, is that basically the default is set to auto, so it recognizes that we're just measuring voltage right now. But you could go, for example, to ohm meter, and it's basically going to say 0 ohms, and we're waiting for data. And so there's a lot of niceties like that that are going into the Cyberscope, so that it's a tool that's hopefully somewhere in the neighborhood as good as the python.microbit.org online editor. I'm really impressed with this editor, and so I'd like to do it justice by doing a similarly good job with the Cyberscope. Oh, let's see. Yeah, we can leave that site. All right, so back to the voltmeter. And the next thing I'm going to do is, and for any of you who use the IPEVO document cameras, I've been noticing that Chrome Web Serial and also the microbit editor don't play all that nice with the IPEVO software. So what I'm going to do is I'm going to show you my camera through another piece of software called VLC Media Player. And it'll take just a second to set up. The first order of business is to turn off my video. So I'm going to stop my video. And then VLC Media Player is coming up. All right, here we are.
Andy, while you prep that, Tommy and I are just noticing how easy it is you've made this multimeter to be used. You wrote a module for it and you just include it, and then it intercepts the data and graphs it or displays it.
Yeah, thank you. I forgot to mention that. There's a multimeter module and we import that. And then the reason that it's a hex download is because basically in a hex file, it allows me to store the multimeter.py module right inside the file. And then that way we don't really have to constantly remind students, and students don't have to constantly repeat the step of adding that file. Okay, so this takes a second, but it's going to be worth it because it'll essentially allow the document camera demonstrations to happen. So open from capture device. And some of you might benefit from seeing this if you have an IPEVO thing and are doing remote stuff, because let's see here. Let's do 1080p. And that's going to be 16:9. Play. Okay, that's scary. Let's try one more time. Let's see here. Open capture device. Ken watched me do this. Okay. When in doubt, unplug and replug the device, I guess.
Yeah, IPEVO is an absolute troublemaker with Zoom.
Yeah, well, or rather, yeah, I don't know who is the biggest troublemaker, whether it's Zoom or IPEVO.
Right.
They each blame each other.
Yeah.
One of them should be quarantined.
Okay, so. All right. One more time. Yeah, this just goes to show the best laid plans. Because I did this. This is like the third time I've done this today. And the first two times went swimmingly. Video device name. That one. No mic. Looks like we're in business. So here we have our nice little LED circuit, and just need to find the Cyberscope. I think it's right there. All right. So when I connect again, I wonder if I have two instances of it open. Yes, I do. Okay. All right. Okay, that's interesting. I am guessing that, and by the way, this is why this is a preview, is it's definitely not the final product yet. Please do keep that in mind. Okay, there's the voltages coming through. All right, so these are the kind of things that I basically watch for as I'm developing the documents. I'm not used to watching for and finding them the hard way as I'm presenting, but that's probably the way it's going to be. And so after this session, I'll be going back and saying, okay, how did I make that happen? And then try to find out what's causing that so that we can basically make sure it doesn't happen for students when this is released in June. Okay, so here we are with our light circuit, and I'm going to adjust it slightly so that it's connected to I want to make sure I've got the right microbit here. Okay, and yeah, that's the only one, and it's showing me voltage now. Oh, the thing I was concerned about was that I wasn't seeing the light come on. Now the LED light is on. And so here is the example of measuring the voltage across the resistor. And so this is a 220 ohm resistor, which was from a previous lesson where we talked about resistor color codes. And the students also know that they picked out a 220 ohm resistor. And so then after taking this measurement of roughly 1.28 volts, and I want to mention that this voltage is bouncing around because of an issue with the microbits A to D that they are currently working on. I reported it, and so that the developers know about it. I also reported an issue for version 2 with the servo control, and that they worked on and they fixed, and you'll get to see that today in not too long. So coming back to the lesson here, after taking some of those measurements, the students can get familiar with it's called Ohm's law for those of you who have never done electronics before. And it's basically, if you have a voltage measurement, you can calculate current by dividing your voltage by the resistance. So it would be one. Yes?
Are we on my Zoom?
Okay, so that's an example of a little piece from measure voltage, and these are, by the way, somewhat skeletal at this point, so I added a whole bunch of them. And so this is an example of one of them. And the most important thing I want you to remember is that you've got these hex files that you can download and then open and try. And then as this lesson grows, one of the things that each lesson is supposed to do is have it so that the students, after they've downloaded and tried something that works, they have to put their hands on the keyboard and modify it to do something else. All right, any questions before we move on to resistance real quick? Okay, do feel free to jump in, and then either Ken or Tommy or both will let me know that a question came up.
There was no resistance.
Andy, we had one question come in. I've only tried this on Chrome. Have you tried it on the latest version of Firefox? I know that this all relies on Web Serial.
It does rely on Chrome Web Serial. I have not tried it on Firefox. And as a matter of fact, one of the things on my list is to basically on the homepage for Cyberscope say you should be using a Chrome browser to do this. Firefox has been doing a good job with some of the other Chrome apps, so we'll see, but I don't know at present.
Yeah, I put this in chat, and it's my own personal belief. I think Firefox will hold true to the Web Serial API standard, so it should work. These are my fingers crossed. It would work so long as it does get implemented properly, and that Google hasn't done anything with Chrome that steered development wrong. So it should work, but it's still TBD right now.
Yes, yeah, I have not honestly tested it. Yeah, thanks for mentioning that. I will definitely check it out. All right, so measuring resistance. So back with, I actually skipped a step where we put in some 3-pin headers and some clips. Was that visible, Tommy, when I did the measurements? So basically, these 3-pin headers right here are for the voltmeter and or oscilloscope probes, and then these two 3-pin headers here and here are for the ohm meter probes, and so that's what the activity is going to have you do, is add in a 2K resistor, which is a convenient value for measuring the resistances that are in the parts kit that are going to be commonly used. And then once you put your clips on there, you can start measuring resistance. Now, I'm making a big mistake here because measuring resistance in a live circuit isn't going to work, and measuring a resistance in a circuit at all is not going to work. So we'll take those apart and pull out the resistor and put it. Now, although this is the way it shows it in the tutorial, something like this, where I've got the resistor just in its own rows, only sharing with the ohm meter probes here and here. You could actually just take the alligator clips and grab each end of the resistor to take the resistance measurement. That's also, it's really, it's pretty much the way I've always done it. So what this shows is how to set up your ohm meter circuit. And notice that I'm making sure that the students can get a good look at that circuit so that they can connect it just so, because pretty much, well, I've seen a lot of mistakes on where the wires are plugged in, and it ends up oftentimes leaving students and or teachers a little bit scratching their heads until they figure out what happened. And so this will hopefully remove some of that pain. And so this is showing right here, okay, you've clipped onto your 3-pin headers and you've set it up so that you have a couple of rows to plug whatever test resistor you want to in. And then you're testing it. And So, and incidentally, the schematic is always shown for whatever test is being done. And also the result, the expected result is shown. If you noticed earlier, I did some animated GIFs where it showed the schematic, it showed the breadboard here, the wiring diagram, and it also showed a little cutout of the Cyberscope, and that's what I intend to do here. But in this initial skeletal part of the document, I instead just pasted them in with, as complete images for the Cyberscope and the circuit/schematic. And so we'll go ahead and merge those two together. And so just a quick example on that then. So here we are. Oopsie. So going back to the instructions, we have a script. It tells you to download a hex file. Okay, so there I downloaded it. And so it's right here. And then sorry about that. Okay, here we are at measure resistance. So I use this link to download the script. And then the next thing to do is go to the Python editor. And then we can load the script by dragging and dropping it into the editor. And then connect, flash, and disconnect, and then look for the Cyberscope window. Here we are. And connect and see if it comes up. It should have just gone straight to the ohm meter. I don't know why it didn't, but that's another thing I'll be looking for. And so the resistor I put in there, it has a color code of red, red, brown, and that's 22, and then the number of zeros is 1. So that's 220 ohms. And so here we're looking at 225-ish ohms, and it's a 5% resistor. So we've got really plus or minus 11 on the value. So it's in range. And so that's an example of using the ohm meter to take a measurement. Again, these are not perfect demos and these are not perfect documents because this is a progress update of curriculum that's going up in mid-June. And so this is, just want to remind everybody that this is kind of an interim. Here's for anybody who wants to try as an early adopter, try it out, send us feedback. Here's how to use the documentation and the tools. So let's see, is there anything else I want to talk about with, there are instructions for downloading the script, and then it takes you step by step through the tests. And then at the end, I also have some notes to self about things I want to make sure to incorporate into the expanded version of this little skeletal piece O document. And now let's move on to current. I don't think I'm going to belabor this one because actually I do want to belabor it for a very strong reason. Hopefully you notice that the rules are a little bit different for voltage and current. For example, and for resistance. So with resistance, the rule is that you have to take the resistor out of the circuit and just measure the resistor to find out its resistance. The rule for measuring voltage is that you can probe it in circuit while the circuit's live. The rule for measuring current is that you have to actually insert the ammeter, that's the device to measure current, into the circuit so that the current flows through it and it can measure the current. So let's take a look at that. building the ammeter circuit, it's a little bit different. Here is the modification. So the 3-pin headers are what we put our clips on if we're going to measure voltage with this. To measure current, we add a, turns out that for the values we're using for the LED, a 20 ohm resistor is handy. That's not actually the way it's done in a real ammeter. They'll either use an ultra small resistor or they'll actually use induction to cause a needle to deflect if you're using an older meter. And so this is kind of an approximation of an ammeter, but it's good enough for what we're doing. And
it gets the point across to the students.
Yes, it does indeed. And so what's going to be happening here, and again, we have a close-up of adding that 20 ohm resistor. And one of the video clips that I have planned is one that's showing electrons flowing. And instead of flowing through the LED circuit like that, the electrons actually flow up the black lead through the 20 ohm resistor, back through the red probe, and then through the light and to the positive. So so that's how current measurement works. And notice that this this black wire is not connected to the LED. It's connected to another row so that the current can go from ground through here and then back up to here and through the LED circuit. And this is one of the reasons why we took so much time to talk about how electrical connections work on the breadboard, is to hopefully help clarify this for the students as they're going through and learning this part. Do we want to just skip the actual current measurement demo? I kind of feel like I'm hoping we're okay. We can do it or not. Does anybody have an opinion?
Yeah, I think for the sake of time, we'll. This is me saying, yeah, mule.
Okay.
I think for the sake of time, I think we understand the concept of it, and of course, kind of doing it yourself is where a lot of the value comes in.
Yes, agreed. And another note is that it'll refer you to your setup parts, and then for this we only needed one extra part on top of that, the 20 ohm resistor. And then another thing, where is it? Here's the circuit. Now, after the circuit, there's always going to be a script. So that's where you load it into, open it with the online Python editor, and then load it, disconnect, then go to Cyberscope, connect that, and then see the ammeter. So it's the same basic pattern for all the tutorials. Is you're going to have parts, circuit, script, and tests. And there's also some other stuff like, if I'll throw in a try this if I know exactly what I want to have, but that's not really necessarily part of this pass. I'm still just populating the lessons. Okay, moving on to blinking the light. And so again, we'll download a hex file and verify that the light blinks. And we also make it blink very slowly to see that there's about 2.7 volts. The IO pins can't quite push the whole 3.3 supply through when they're under load. So we see about 2.7 volts. And so students actually measure the voltage when the light is on and the voltage when the light is off. Additionally, they connect it to the oscilloscope. And this is, Tommy, where I was referring to going back in time to retroactively make the correction, because as may be apparent here, we have a signal that kind of starts here and it goes a little ways back in time before before it goes to its high signal. What this is basically the graphing API that I used while writing this. Has a smoothing feature. And I thought I dialed it back enough to make sine waves look good and exponential decay look good, but still have digital signals look okay. But I think I need to back it off a little further because this smoothing is not working out for the digital signals. So that's something that's going to be adjusted here, hopefully fairly soon.
Or maybe we just have Doc Brown from Back to the Future say something about
a however many gigawatt capacitor. Okay, so let's try that one. So here's LED blink with plot. Download it. It appears over on the left here. Then we can go to python.microbit.org. I'm sticking with the beta. Drag and drop it onto the editor. And another quick heads up here. Initialize display is something that I'm doing right now to prevent display freezing when it gets too much data. It's something that, before June, what we want to see is if it's receiving a fire hose of data, that it can either selectively discard that data or tell you that it's not ready, or basically something to handle it gracefully. Currently, it does freeze, and that is a heads up for earlier adopters that they may have to refresh their page and reconnect if they send too much data without first setting up the oscilloscope to display said data. Now, the script starts out, I should probably show you how the script starts out. Okay, so we're going to also get just plain old blink.hex. All right. So here is blink. And so this is what turns the light on. That's what keeps it on for a little while, the sleep 250. Then this turns the light off, and this keeps the light off for 3/4 of a second, 750. Now, compare that to the scope version. What I did in order to plot it is I said, plot the volts measured at pin 2 before turning the light on, immediately after turning the light on. Then we can sleep, and we don't need to really check the voltage during that sleep time. Then we plot it before and immediately after turning it off. And so those are 4 calls to plot volts that the student can add basically before or after digital high-low events in order to get it plotted. Flash. Disconnect.
Andy, question from the viewers. Where is the API for the multimeter and the oscilloscope?
It is in my head.
Okay, thank you.
It is in my head, but it will be published soon. It's on the list along with a whole lot of other writing that has to go on over the next couple months.
Do it in your order. Thanks.
Okay. I don't know if we want to keep a mailing list and just send out an update when. Well, that doesn't look like I really expected it to. Huh. Oh, okay. Well, let's take a look at why.
Someone should guess. I think we may have seen the reason.
I kind of feel like I know the answer. of why we're just seeing noise. Does anybody want to hazard a guess? Okay, well, I'll just spoil it for everybody. I hadn't really connected the probes yet. So
They're just kind of floating out there.
yeah, and also the circuit, I really wasn't following the instructions as carefully as I needed to. So I believe that I'm hoping that now I have a blinking light. Yes, I do. So there's the blinking light. So now let's go back to the scope and see if we have our Back to the Future binary signal here. And there are instructions, and I forget where they are, but you can zoom in and out of the time base. That's something that I'd really like to make clear, is that this is a little bit more than just a plain old graphing utility like the one you might find in Mu, for example, in that it is emulating an oscilloscope. And so you can, for example, select a trigger, and that trigger gives you the ability to cause an event, one of these lines in the graph, to pass through where our time here and our voltage here intersect. So it should update in another couple there. It went ahead and synced up with it, and I can move it a little bit more and it'll sync up again. And the one enhancement that is kind of a must for this is that I want to, similar to the trigger, have the ability to drag these guys around or and actually take time and voltage measurements by having a pair of these crosshairs, a pair for measuring time differences and a pair for measuring voltage differences. That's one of the things that we're trying to add in the next sprint on this software. All right, so that's, also, so here we have high for half the time and low for half the time. And the plan is to challenge students to change it up a little bit. Okay, so I just made it high for a short time and low for a longer time. And it'll take a few seconds because there we go. And so now you can see that it's high for a shorter time and low for a longer time. And one of the things this does is it segues into the signals that are used to control servos, because they are brief pulses that are spaced relatively far apart. They happen more quickly, and the pulses last for shorter amounts of time. But this gives students a first experience at seeing that kind of data, a visual representation of a sequence of high-low signals, and it also gives them the opportunity to experience that.
Hey, Andy, I have a question.
Yes, Chip.
How come the traces move backwards in some points? Are you using some sort of curve fitting or something to draw the traces?
Yeah, that's exactly what's happening. So I'm going to, that's on my bug list.
Okay.
So what I did was I was really obsessing over sine and exponential decay, and I knew that I needed to have little, if any, curve fitting, but the small amount I chose is clearly still too much.
Okay,
So,
just curious.
yeah, thanks. Yeah, that's what we were joking about with our backwards in time feature. So, yep, that will look very different next time. Okay. Next up is going to be I can get back to the slideshow, here it is. Okay. Next up is a push button. This is a place where push buttons are something that unfortunately folks have learned to use just basically given a schematic and a wiring diagram, and they work okay in inventions, but unfortunately that there aren't many who are able to sit down and read the text and really get what the 1,000 words might be talking about how and why a push button really works and why there has to be a resistor connected to it that's pulling it to ground. Those are things that are not. I've known more than a few engineering students who really hadn't asked themselves, why do they put that 10K resistor between the push button and ground? It just seems like an extraneous part. And so part of the goal in measuring this circuit is to understand that you have two definite different voltages when you're measuring with a push button. And so with this particular circuit, by the way, Tommy, Chip, Ken, is this visible to you? Is it fairly clear? Okay, thank you, Chip, for your nod.
It is. I have a question though.
Yeah.
Why the 220 ohm? Is that just to protect pins or something?
Well, yeah, it's a habit that we developed because back in the basic stamp days, there were a certain number of I/O pins that were burned up by not having a 220, accidentally having a wire, and maybe your code would send high and low signals through the pin. And as soon as you press that button, when the pin is sending a low signal from a previous program, it would pop on a basic stamp. And so we'd end up replacing those at a discount. And so just to try to prevent to try to minimize that, we throw in that 220, yeah.
I see. Yeah. I just think for a kid who's kind of trying to understand this, that he's going to wonder like what the concept is. Should probably be explained a little bit so he knows it's not necessary. It's just a protection feature.
Yeah, and we say that in I believe we say that in all of our books is basically there's a paragraph about it somewhere. I'll keep that in mind as I'm writing this.
Yeah, that's just the difference between like production electronics and theoretical electronics.
Yeah, well, it's also, I mean, in production, you may not need it, but man, for prototyping, it really makes a difference. Okay, so the measurements happen with this button pressed and not pressed, and so that the students get to see, hey, we have 3.3 volts when it's pressed and 0 volts when it's not pressed. And they get to see that also as something where the push button is read straight with the microbit. So basically we get to see, hey, there's voltages that are going to the microbit and we're measuring them. And then in another step, we're writing a script that actually takes and displays those measurements as zeros and ones. And that, of course, gets used for any kind of push button control that is applied later, like our blinking LED. And I'd be remiss if I didn't demo it. Okay. So here's our blinking LED. And so this is where some of the programming lessons come in terms of, hey, we want to say if the state is 1, as we just saw when we pressed the button and held it in the terminal, then make the light blink. Otherwise, don't make it blink. And I'm going to make this 500 and 500 so it's nice and clear on the display. One thing I've been pretty happy with is I believe that the Cyberscope is still connected, but it lets me connect and load code and disconnect. So that's been a pretty nice thing. So now when the button is, so for this, we would take away the probes because it's just an application. And now I'll go ahead and hold down the button. And we've got the blinking and then let go of it and not. And that's a really important lesson. And there's kind of a balancing act between getting to that and taking measurements and learning the theory. And so I'm trying to make the theory a little as light enough with optional deeper dives, as opposed to dragging everybody through all the calculations. The calculations that are used by the measurements appear in an optional link that goes elsewhere. That goes to, I've been calling it an engineering workbook. Okay, so let's see here. Back to the slideshow. Do we have any more questions while I'm making my way back to the slides? Okay, servo position control. This is one where I'm kind of curious now. I'm using the beta microbit editor, basically python.microbit.org/v/beta. And I know that works. I don't know if they've incorporated it into the version 2 editor yet. So we'll see that, we'll find that out right now. So one interesting thing that I did here is to run a servo, the first step is connecting a battery pack. And what's cool is we can use the Cyberscope to probe the battery voltage, which is up here just above the edge adapter. So the batteries plug in below, and then the battery voltage goes to these columns above the edge adapter, and you can use the voltmeter to probe it and to make sure that your batteries are lively enough to run the servo. And then it takes you step by step through setting up a little do-it-yourself servo header, and then connecting the actual servo. And then you're ready to go. Notice I keep, actually this is, I'm gonna need to edit this particular picture because I want the grayed out voltmeter probes to also appear. But I do try to gray out any circuits that we want students to keep, but not necessarily pay attention to while they're building whatever circuit they're working on. In this case, the servo. So then go find the script after you've built the circuit. And same drill, download it, put it in the editor. And then I have to switch out my my board to one that has the battery pack and the servo.
Andy, while you're prepping this, we'll ask any of the teachers here to get any comments, questions, requests, feedback together.
Yeah, now do we want to have it, do we want to have a particular email address for that, Ken?
Well, they could use education@parallax.com, or they can ask questions here too.
Okay. Yeah, well, certainly questions here. All right. So here is our little servo that comes in the kit. And we also have the circuit that was built up right here. It's P16, 220 ohm resistor again, running the signal up to the orange wire. On this servo, red is still positive power, and then brown is negative power. And go ahead and load the code, connect. I plugged in a different microbit and so it was still setting up. Okay, so what this code is going to do is this will turn the servo to roughly, it'll make the servo point at roughly 3 o'clock. The sleep 4000 will keep it there for 4 seconds. This statement will turn it to approximately 12 o'clock. This statement will keep it there for another 4 seconds, and then 9 o'clock, and another 4 seconds, and then it'll repeat itself. And I already downloaded it, so I should just be able to connect the battery. Start seeing it work. The reason it's not doing anything right now is because without the battery, the servo has no power. The power to the rest of the board comes from this 3-volt, 3V pin. And so that travels through this wire, and then it gets distributed to these 2 columns that are next to the red lines. But this column next to the red line only comes from the battery right here. And so when I plug it in, I want to see the servo going through its 3 o'clock, 12 o'clock. Okay, so now it's at 9 o'clock, back to 3 o'clock, 12 o'clock, and 9 o'clock again. And after that, there's a control servo with potentiometer. Actually, I apparently forgot to put the potentiometer link in this slideshow. I'll fix that in not too long. It's potentiometer position sensing. But since we're on the subject of the servo, let's go ahead and just load the pot controls potentiometer script. And then I'll backtrack to lessons that involve a potentiometer, which is a knob you can turn to that can communicate the position you turned it to electronics. At least that's what we use it for mostly. It has a lot of other uses in the electronics industry. Okay, so got my download. Here's the Python editor. Nope, that's not the Python editor. This is the Python editor. Okay. So this script is going to measure the potentiometer, then do a y equals mx plus b calculation. That's very important from the for any of you who need to have a nice concrete example of why the y equals mx plus b that is used in algebra is actually important. Well, here's something that does something with it. And I also, this little piece of code makes it so that when you turn the potentiometer in a direction, the servo turns the same direction. Without it, it turns the opposite direction. And then this piece of code or statement is what actually makes the servo position itself accordingly. Okay, so let's get the potentiometer in view.
So Andy, in the interest of time, I know we have a few folks that may be ducking out here shortly.
Okay.
You mentioned showing the why of MX plus B and, why I need to include all this. That's really what, when we were first talking about all of this is really what we were attacking with the activities is why do we do this and why do we do this? I wanted to also, before folks have to jump off, I wanted to kind of open this up to the kind of the audience here and say, and kind of see what do you guys think? What is of value? What would you like to see more of? And kind of get some, some constructive feedback, I guess.
Now, may I have 5 minutes before we embark on that?
Yep. So get those ideas percolating. How's that?
Thank you. Yeah, in just 5 minutes, I'll be at a good stopping point for that. Oh shoot. Let's see. Can I find a parallax? Where is a parallax screwdriver when I need one?
I got one here.
And
Okay,
while he looks for a screwdriver and sets this up, we should let everybody know that this comes out in the summer. There will be probably 100 or more pages of tutorials, and there is a parts kit for it, which I've previously linked. And each of the pages is probably a 15 to 20 minute project. So likely 40 plus hours of classroom work. And when we're working with something like the microbit, this is always hard for a company to invest solely into because, there's very low financial reason, but we've had the help of cyber.org to fuel us in this effort to get a very good pre-engineering curriculum prepared for this. So we really thank those guys for doing that. And the benefactors will be all of the teachers and students, most importantly.
So hopefully you guys have seen me turning the screwdriver and seeing the servo following the potentiometer as I twist it around.
What I love about this activity, Andy, is that it shows, you got human input and then you see some physical output. And a lot of people would look at it and go, well, it's just a knob turning the device. And we see this on a lot of consumer devices these days, right? You tune the radio knob on your car to tune the radio, but it's not just turning something, used to, there was actually a belt inside the radio that was actually turning a physical capacitor. Now that tuning knob it's controlling a digital circuit that is then responding. Capacitance is still changing, but it's all happening at a chip level. And so here what we've got is with the microbit, the input is being read. That's one lesson. Then you got this other physical output with the servo. That's a lesson. And here we're merging those two together so that you have physical input creating physical output.
And the last thing I wanted to show before we break for the discussion is coming from a second microbit. So what I'm going to do is I'm going to load in a program that, so this microbit is going to, the second microbit here is going to have a script loaded into it that transmits its tilt level. And then this microbit will receive that tilt level and then position the servo accordingly. So to do that, we'll go back to the activity. The pot controlling the servo activity. And down at the bottom, I have a project that refers to a couple of Cyberbot links for examples. And then the challenge is to take the tilt-controlled robot and just make it a simple tilt-controlled servo using the radio and accelerometer that are built directly into the microbit. And this is where, you know, the fun can really start after a few lessons is that the students, after they've built a few circuits, they can start not only mixing and matching the circuits, but mixing and matching some of the other features that are built into the microbit. Okay, so this is the transmit. And I don't know which is which, so I'm gonna try to take a look at whose light blinks as I load the code. It didn't even show me that. Well, I think we'll just take a stab in the dark here and see if it works out. Oh, how about that? Okay, so now, hopefully you can see that I'm going to bring this out a little bit. All right. So do you see that as I tilt the microbit that I'm holding on to, that we get a display response on that microbit that is also mirrored on this other microbit here. And for some reason, the servo is not actually moving. It might be because this battery pack fell out. Okay.
Power is important.
Yes. And then it looks like, okay, now if I have it turned the right direction, you can see the way the armature on the servo, called a horn, follows the direction that I'm pointing the USB cable. Is that visible?
Yep.
And of course, we can put a battery pack in this one too and take it off somewhere else and use it to control mechatronic props and the like. Okay, so that was the thing I wanted to show you, and that puts us at a breaking point before doing some analog measurements using RC decay and sine D to A and A to D. So let's go ahead and open it up for some of the discussion and Tommy, if you'd like to lead any further into bringing up what are you looking for your classroom?
Yeah, so I guess kind of kick that part off. Wondering, what courses are you teaching this? What context? So you could be using this in physics, or in what Andy just showed us with the tilt sensor and having it done remotely with a servo. There's no reason you have to use that particular servo. You could use a larger servo, so long as you have enough juice to power it. But you could control seemingly anything. So even a theater class could still benefit from knowing, having this know-how. You've got some kind of stage prop you need to trigger at a certain point. You can do that with a kit like this. So obviously physics works into it, computer science and programming and kind of engineering course works into it. Are there any courses that you're teaching that maybe you're having a hard time shoehorning the projects that we have outlined for you into your courses? Is there is there a gap that you are seeing in the content that you would like to see filled? How can we better serve you? Open that one up. Not all at once.
Well, I'll just tell you that we have a real issue. It's not one you have to shoot into, it's a perfect fit. But I teach both robotics and electronics at one of our schools and electricians at another school. And I'm constantly telling the electricians that they need to become more computer conversant. And this looks like a perfect tool when the software is up and running for me. And they have no lab associated with the one for the electricians. So this might be a perfect tool for them to be able to get in and make the measurements in a low-cost fashion, and also segue them into learning something about processes, which I've been trying to drum into their head. So I think it's a real benefit for us. So thanks very much to you and to Andy, Ken, and Chip for doing all this for us. Thank you.
Thank you for that.
And I will acknowledge that Andy has been the I was joking calling him the mule earlier, but he has been completely carrying this load on his own while I've been working on some other initiatives and efforts that we've got. So total kudos to Andy for developing this and the team at Parallax. There's Kevin.
Hey y'all, this is Kevin. I just wanted to jump in and echo my appreciation and my thanks both to Ken and Andy for all the great work. Tommy from my team, who's been in the trenches with this. This is an awesome project, an awesome initiative, and from a cyber.org standpoint, this is huge. This is big, and for us to be able to enable our teachers and our students with these kinds of skill sets, we're able to educate and generate the next generation of cyber literate workforce, and that's my goal. And I know my friend Ken and I are always talking about ways in which we can expand and continue the great work. So Andy, thank you for putting all this together, and Ken, Tommy, thanks for being a great partner and throughout this whole entire process.
And the introduction after the fact, Kevin Knowlton, the director here at cyber.org. So that's who. Since it doesn't have it on his name there. who is that guy talking?
Well, thank you, Kevin. This has really been a great project. One of the things that I've always felt was a missing piece in electronics education using microcontrollers is simply having some built-in measurement equipment. And so this has been very exciting to be able to finally add that component in and have it be something that the students can use and just give them a more complete picture. And also, in my mind, to open up opportunities to use the math that they've been, struggling through in algebra, and to be able to gain a more complete understanding of what's happening in each circuit. Both of those things are things that being able to invest in this kind of built-in measurement equipment that becomes part of the kit has been it's been very key. And so thank you, cyber.org, for your support. We're going to make this the best we can possibly make it. And with that, let's continue back to the feedback section. Share screen. All right, here we are. So yeah, it's a little disconcerting to get nothing but assent. We need some guidance. We need, hey, I have this pet project. Could we see that? Could that be a possible candidate for the lessons? How about that one?
Or the other thing I like to say, it's a little tongue in cheek, but when asked for feedback and we hear a bunch of kudos and such, we do appreciate that. I'm not gonna trounce that. We do appreciate the kudos and we love to hear it. But when it comes to feedback, also when people tell us at cyber.org that, we love your stuff. It's perfect. I'm like, well, we know it's not absolutely perfect. We can always grow some more, but we want to hear criticisms. Criticisms are not negative. If you can tell us that something sucks, we'll still take that and run with it. But tell us why. How can we meet your expectations? And if there's any kind of shortcoming, Ralph's talking about with the electricians and such, making sure that we cover that audience is something that's of value too.
If you have some way that you could show how your microbit might control some device. I'm constantly telling these guys and ladies that there needs to be a way to control every building now that is going in as a smart building. And if you have something in there to control a device that will actually control an electric light, if you show them a relay or